Hello friends, welcome to my video. Here I will explain the position of the Fermi energy level of an intrinsic semiconductor. In case of intrinsic semiconductor, the Fermi level lies between the conduction band and the valence band. That it lies exactly in the center of the conduction band and the valence band. First of all, we will define what is Fermi level. Fermi level can be defined as that level which has 50% occupancy of electrons at that particular temperature. This level lies between the conduction band and the valence band, that is, it can lie anywhere within the energy gap. Now we have two types of semiconductors, that is the intrinsic and the extrinsic semiconductors. One of the most important properties of a semiconductor is that it can be doped with a p-type material or an n-type material. When these impurities are ionized and the carriers are depleted, they leave behind a charge density that results in an electric field and sometimes a barrier potential. The three basic bond pictures of a semiconductor here we have taken in the first figure, that is the intrinsic silicon semiconductor without any impurity. In the second figure we have taken a silicon with an n-type, that is we have added phosphorus which is pentavalent and therefore excess of an electron. In the C-type figure we can see it is a p-type silicon where the silicon is doped with a boron, that is a trivalent having excess holes. In the phosphorus that has a 5 valence electron has replaced a silicon atom and a negative charge electron is donated to the conduction band. The phosphorus atom is called the donor. Whereas the boron has 3 valence electrons, a positive charged hole is created in the valence band and this boron is called an acceptor. This is the energy band diagram of intrinsic and extrinsic semiconductor. We can see over here in the intrinsic semiconductor, the Fermi level is in between the conduction band and the valence band. In the n-type semiconductor, we can see that the Fermi level is near the conduction band, whereas for the p-type semiconductor, the Fermi level is more towards the valence band. Here we are interested with the intrinsic semiconductor where the Fermi level is in between the valence band and the conduction band. Before we start with the derivations, we will assume that the width of the valence band and the conduction bands are equal, and the second is that the energy gap is large as compared to the width of the conduction band and the valence band. Now we start with the derivations. Here we have taken Nc as the number of electrons in conduction band, Nv number of electrons in the valence band, N total number of electrons, that is N is equal to Nc plus Nv. The probability of occupancy of electrons in the conduction band, that is given by PCE, is equal to Nc upon N, where Nc is the number of electrons in conduction band divided by total number of the electrons. Now we can write that Nc is equal to PCE upon N. Similarly, we can write the probability for the valence band, that is PV is equal to Nv upon N, that is number of electrons in valence band divided by total number of electrons. Nv is also equal to PV upon N. Using the Fermi Dirac distribution, we have PC is equal to 1 upon 1 plus E, EC minus EF upon KT, where Nc is equal to N upon 1 plus E, EC minus EF upon KT. Similarly, we write for the valence band the probability, that is PV is equal to 1 upon 1 plus E raised to EV minus EF upon KT. NV is equal to N 1 plus E raised to EV minus EF upon KT. The difference is only that it is EV minus EF for NV, and for NC it is EC minus EF. We add both the equations, that is NC plus NV, and then we can see that we get a common N. Therefore, we can write 1 is equal to 1 upon 1 plus EC minus EF upon KT plus 1 upon 1 plus EV minus EF upon KT. Taking the LCM, we have to multiply the denominators and we have to add the numerators. So we have added and multiplied. After solving, we get that E is raised to EC plus EV minus twice EF divided by KT is equal to 1. Taking log of this, EC plus EV minus 2EF upon KT is equal to 0. Solving, we get EF is equal to EC plus EV upon 2. Thus, we can say that the Fermi level in an intrinsic semiconductor lies between the conduction band and the valence band. It lies exactly in between the conduction band and the valence band. Thank you for watching this video.